Now we are going to talk about the rating of a transformer. Suppose this is a transformer with two windings. This is the primary winding, suppose, and this is the secondary winding. In this diagram, I have shown the two windings on two opposite sides or arms of this core, but normally in an actual transformer, the primary and the secondary winding are not placed separately on separate arms. Normally they are together, one on top of the other, maybe like this. If this is the primary winding, the secondary winding may be on top of the primary winding, and they are of course insulated from each other. They are electrically separate. But anyway, for clarity of drawing, let me draw them separately. Now, if I say that the rating of this transformer is 200 volt by 500 volt, okay, that means this is the voltage rating of this transformer, 200 volt by 500 volt, which means this transformer is manufactured, designed to work with 200 volt across the primary winding and 500 volt across the secondary winding. We cannot use this transformer with any higher level of voltages, because if we do that, the transformer may get damaged, it may cause dangerous accidents. Why? Because if these two ends of this winding are at two different voltages, suppose this end is at 0 volt and this end is at 200 volt at some point of time, that means the in-between turns are also at different voltages, like for example, this turn, this point may be at say 80 volt, this point may be at say 160 volt, and this may be at 200 volt, and so on. So the different turns of this winding or this coil, they are at different potential at all the moment, and therefore we need to put some insulations between the turns so that they do not short each other. There is no short circuit. So that there is no short circuit, we must have some insulations between turns. Okay. Here also we need some insulation for this winding and so on. Now, any insulation can withstand up to a maximum level of voltage. Okay. If you want to withstand more voltage, you may need to provide more insulation, thicker insulation. But if this transformer is designed for 200 volt by 500 volt operation, then if you apply higher voltage, if you work with higher voltage, then these insulations, inter-turn insulation, and also insulation between the coil and the core, they may not be able to withstand the higher level of voltages. There may be a spark or flashover through the insulation, which may damage the transformer, which may cause dangerous accidents. So we should operate not beyond the specified or rated voltage for a transformer. Similarly, the windings, the coils or the conductors of a transformer can carry up to a certain amount of current. Okay, how much current can this coil carry? That depends on the thickness of the conductor. For more current, we need thicker conductor. So therefore, the coils have a current rating beyond which we should not operate, which may cause overheating and which may damage the equipment, which may cause accidents. So there are also ratings or maximum levels of current which specified for these coils. Now, normally the current rating of a transformer is not directly specified. It is indirectly specified. Okay? So current rating is normally indirectly specified by or through the specification of volt ampere rating, through volt ampere rating. Okay? So suppose if I say that this is a 2 kVA, 2 kilovolt ampere transformer, that will indirectly specify how much current the primary winding and the secondary winding can carry at max. Okay? So for example, in this case, maximum primary current maximum allowable primary current will be equal to 2 kVA, that means 2000 volt ampere divided by the rated primary voltage. Okay, so which in this case is 200 volt. So that means it can carry at max 10 ampere current. The primary winding can carry at max 10 ampere current. Similarly, maximum allowable secondary current for this transformer will be equal to 2000 volt ampere divided by secondary voltage rating, which is 500 volt, that means 4 ampere. Okay? So if we operate this transformer beyond these specified levels of currents, the transformer may get damaged, it may cause severe accidents. Now, the third important rating about a transformer is the frequency rating. Okay, so for example, I can say that this is a 200 volt by 500 volt 2 kVA 50 hertz transformer. Okay, what does this mean? It means this transformer is supposed to work under 50 hertz frequency, and normally we can increase the frequency, but we should not decrease the frequency. Actually, this frequency rating comes from the maximum flux that can flow through the core. Okay, so the frequency rating is determined or governed by the maximum flux through the core, maximum core flux, magnetic flux. Okay, so let me explain this a little more. If we apply a source, okay, to the primary side, let the secondary side be open for simplicity. Now there will be some current here, call that current I, and if this current I increases, then let me call it I, then the flux through the core will also increase as this current I increases. Okay, so we have phi core flux proportional to I. Okay, and the relation between the voltage and the flux we have studied earlier. If this voltage is V, call it Vs, supply voltage, then the RMS value of the supply voltage is given by root 2 pi phi, RMS value of phi. So let me write RMS sorry, not RMS value of phi, maximum value of phi, peak value of phi. Okay, so Vs is root 2 pi phi f times n, where n is the number of turns of this coil. This relation we have studied earlier. Now, for a given amount of supply voltage, okay, for a given value of Vs RMS, if we decrease frequency, if we decrease frequency f, then we need more flux, we need more phi max or peak value of the core flux. So the flux will increase if we decrease the frequency for a given or constant value of the RMS, constant RMS value of the supply voltage. Now, there is a relation between the current and the flux. Okay, so we can draw a graph showing the relation between the current I and the core flux phi. Okay, so if we increase I, the flux will also increase. And normally the permeability of a good transformer is assumed to be very high, so therefore the flux increases very fast compared to the current. Okay, so flux increases very steeply, assuming the permeability to be very high. So mu is very high. However, after a certain point, the flux will not increase much or will not increase significantly. After a certain point, the increase of flux becomes very slow. So it becomes almost flat, almost horizontal. Why does that happen? This is because, as we have seen, this core, the magnetic material, is made up of small tiny magnets, and when we apply current, the magnetic field tries to align all these tiny magnets along the direction of the magnetic field, and these tiny magnets, when they are aligned with the magnetic field, they increase the flux to a huge extent. However, after a certain point, when all the tiny magnets are completely aligned, then even if we increase the current, there are no more tiny magnets left unaligned, so they cannot get further aligned, they cannot increase the flux anymore. However, flux will still increase. It will increase at a slower rate because anyway, even if we do not have any magnetic material, even in vacuum or air, when we increase current for a coil, the flux increases, but that increases very small. So after a certain point, the flux will not increase much. Actually, the graph will look a bit smoother like this. This portion is called the air line or the saturation region. Okay. Now, a transformer is designed to operate near this corner point or knee point. Okay, so normally the transformer is designed to have the flux value equal to or close to this corner point or knee point. And then flux and voltage, they are proportional to each other. So this point corresponds to the rated voltage. Okay, so the flux value at this point will correspond to the rated value of the voltage. Now, when there is no load connected to the secondary current is 0, then when the primary voltage is applied, how much current flows through this coil, that is determined from here like this. So if I drop up a vertical line, then this current, this amount of current is the current that flows through the primary coil under no load condition or when secondary is open. So this is the no load current Okay. So a transformer is so designed that it has a very high permeability. So initially this graph is very steep, almost vertical, and the voltage rating of a transformer is such that if we apply rated voltage, the flux level will correspond to this value, and under that situation the current that the transformer will draw will be this much. So this is a very small amount of current because this graph is almost vertical. So no load current is very small. But now if we decrease frequency, if F is decreased, keeping Vs unchanged, okay, then we need more flux, then we need more flux. Okay, so suppose I decrease the frequency and now we need more amount of flux, maybe we need this much flux. And to get this much flux, how much current do I need? So for that, let me extend this line horizontally. Now, wherever this horizontal line cuts this flux current graph, so that may be here. Now, if I draw a vertical line from here, this will represent the required amount of no load current required to get this higher value of flux. So we see now we need a very large value of no load current to operate this transformer at a lower frequency. So therefore, we should not operate a transformer with a frequency lower than the rated frequency, because then we need a very high amount of no load current, which may cause damage, or even if it doesn't cause damage, anyway, the assumption that for a good ideal transformer, no load current should be close to zero, should be very small, that is violated. So that's a problem. Okay. Now let's take an example. Suppose we have a 24 kVA 60 Hertz transformer which is used in a 50 Hertz power system. Under this situation, what is the maximum amount of kVA that this transformer can handle without increasing no load current? Okay, so we know the relation between the voltage, RMS value of voltage, and the flux is like this. Vrms is equal to √2 pi phi max. That means peak value of flux. Okay, then n number of turns multiplied by frequency f. This flux is a function of the current, or say no load current. We don't want to increase no load current, that means we cannot increase this flux. So therefore, this part is kept constant, kept unchanged. But this frequency is reduced by a factor of 5 by 6, 50 by 60. Therefore, we cannot apply full rated voltage. We also have to reduce this maximum applicable voltage by the same factor as the frequency. So this should also be reduced. So therefore, the maximum allowable voltage, okay, becomes max allowable voltage, or you can say the new voltage rating becomes 50 by 60 times the original voltage rating. Okay. Now, what is KVA rating? KVA rating is the product of voltage rating multiplied by current rating, voltage rating and current rating When I say current rating, I mean the on-load current. That means the current that will flow, that can flow if the secondary side is loaded. Okay, and there is no change in the current rating in this case, so this is unchanged. But the voltage rating is changed, and the new voltage rating is basically 5 by 6 times the original voltage rating. And the current rating is unchanged. Therefore, the new KVA rating will become 5 by 6 times the original KVA rating. Now, original KVA rating was 24 volt ampere KVA. So the new KVA rating will become 5 by 6 into 24 KVA, which is 20 KVA. Okay. Here is one more example that we will solve. We have two transformers connected one after the another. This is called an cascaded connection. Now the ratings of the two transformers are given. Okay, this is 240 by 4800 volt 9.6 kVA transformer, and this is a 4000 by 200 volt 12 kVA transformer. Now we have to find that how much can be the maximum supply voltage here, so that neither of these two transformers exceed their voltage rating. Okay, so you see the maximum allowable voltage between node A and B is 240 volt, and if we apply 240 volt here, then between nodes C and D, the voltage will become 4800 volt, 4800 volt. However, the maximum allowable voltage between the two ends of the second, the primary of the second transformer is 4000 volt. So therefore, we cannot go up to 4800 volt. So this must be at max 4000 volt. Now, if the secondary voltage of the first transformer is 4000 volt, then how much should be the primary voltage of the first transformer? Okay, so the voltage ratio is given here. So therefore, Vs, the primary voltage, should be equal to maximum secondary voltage 4000 volt multiplied by the voltage ratio or turns ratio of this transformer, which is 240 by 4800. So this is equal to 200 volt. So that means we can apply maximum 200 volt at the primary of this first transformer. If we apply any larger voltage, then the voltage rating of the second transformer will get exceeded, which is not allowed. Okay, so the first question asks how much is the maximum allowable voltage of Vs, and the answer is 200 volt. Next, in the second part, we ask how much is the maximum value of the supply current Is, that means this current that we can allow so that neither of these two transformers exceed their current ratings. Okay, now current ratings are not given, so let us find out the current ratings. So primary current rating of left side transformer is how much? KVA rating is 9.6 kVA, so 9600 volt ampere divided by voltage rating here is given 240 volt. So this will give me the current rating of the first primary current rating of the first transformer, left side transformer, which is 40 ampere. Now similarly, secondary current rating of the left side transformer will be KVA rating divided by the rated secondary voltage. Rated secondary voltage is 4800 volt. Okay, 4800 volt. So that is 2 ampere. Similarly, the primary current rating of the right side transformer is how much? The KVA rating is 12,000 volt ampere divided by the primary voltage rating of this second transformer is 4000 volt. So that means this is 3 ampere. And similarly, the secondary current rating of the right side transformer will be 12,000 volt ampere by secondary rated voltage is 200 volt. So this is 60 ampere. These are the maximum allowable currents in the primary of the first transformer, secondary of the first transformer, then primary of second transformer, and secondary of the second transformer respectively. Okay, so now we see that here maximum allowable current is here the maximum allowable current is 2 ampere, but here the maximum allowable current is 3 ampere. So which is the minimum of these two, that is 2 ampere. That means the maximum current that can flow here is 2 ampere. Since the secondary of first transformer and primary of second transformer, they are connected together, so the maximum allowable current here is the minimum of 2 ampere and 3 ampere. So this is the maximum allowable current here. Now if this current is 2 ampere, how much should be Is? Okay, so Is therefore should be max value of Ix should be equal to this 2 ampere multiplied by the ratio of the turns of this first transformer, which is 4800 by 240. This is the turns ratio of the first transformer. So this comes out to be 40 ampere. Okay, so then this is the answer. So this is the maximum value of IS that we can allow without exceeding the current rating of any of these transformers. Okay, so the answer is 40 ampere for this second part. Now the third part asks how much is the maximum kVA that can be transmitted to the load, that means here to this load, without exceeding any transformer rating. So we saw that a max value of the supply voltage Vs which is allowed is 200 volt, and maximum value of this current is 40 ampere. So that means maximum kVA that can go from the source side to the load side is 40 ampere multiplied by 200 volt. So 200 volt into 40 ampere, which will be 8 kVA. So you see the maximum kVA that can be handled by these two transformers connected in cascade is 8 kVA, is much smaller, is lower than the kVA rating of the individual transformers. Okay, but this is the maximum kVA that can be handled by these two transformers together. This is the answer. Okay, now one thing you can check, okay, is the kVA balance at different points in this circuit. Okay, so let us just check the kVA at different points. So the kVA volt ampere supplied by this source is, okay, so at this point, at this port AB, okay, so at AB, okay, kVA supplied by source, as we have already calculated, is 8 kVA, which is equal to 40 ampere multiplied by 200 volt. Then when this Vs is 200 volt, then the voltage between C and D is 4000 volt, and if Is is 40 ampere, then the current flowing here is 2 ampere. Okay, so therefore in this region, in this part, CD, okay, so at CD, kVA going from left to the right transformer is equal to 2 ampere multiplied by 4000 volt, which is again equal to 8 kVA. And then finally, if I call these points as E and F, then here in this region EF, the kVA that is going from the second transformer to the load, okay, so at the region EF, kVA drawn by the load is equal to how much? For that we have to find how much is the voltage between E and F and how much is the current here. Okay, now looking at this second transformer, the turns ratio of the second transformer is 4000 by 200, that means so this ratio is 20:1. So if the primary voltage of this transformer is 4000 volt, then the secondary voltage will be 200 volt. Okay, and similarly, if the primary current is 2 ampere, then the secondary current will be 20 times, that means 40 ampere. So once again, the kVA drawn by this load is 40 ampere multiplied by 200 volt is again 8 kVA. Okay, fine.